Hello student, tonight from your textbook, which is Calculus with Applications, I'm trying to discuss one of the application problems, which is called Elasticity of Demand. To discuss elasticity of demand, we need to define a function. Let function q is equal to f of p, where q is the demand, at a price p. Then the elasticity can be defined, elasticity, which we denoted with capital E, can be defined as E equals to minus P divided by Q times dQ over dP. This means only P over Q, and this is the derivative of Q with respect to P. So you have function P over Q, and then you have the derivative of Q with respect to P. In other words, if we have a function Q in terms of P, which we have this function, is given to you. Therefore, we should be able to find this, which is the derivative, take the derivative of this, and multiply minus P over Q. That will give you a function is called elasticity. And this elasticity has three different cases. First case, when E is smaller than 1. Second case, when E is greater than 1. Third case, when E is equal to 1. So there are three cases actually. In case E is smaller than 1, we say that the demand is inelastic. So in this case, when you got E, any number is smaller than 1, then we say demand is inelastic. Later on, I will show it to you with the picture. Perhaps you understand it better. Second case, when E is greater than 1, then we say that demand is elastic. Third case, when E is equal to 1, the demand has unit elasticity. So in this case, we say that demand has unit elasticity. Usually we start from case 3 to solve a problem. I will show it to you later on, to solve a problem in a numerical case. So this is in general. In numerical example, I give it to you. We start from here, then we go to see whether we are in the first case or the second case, and we will find whether our demand is elastic or is inelastic. Then I'll show it to you also by the picture. For instance, here I have a problem that we can work on it, and that is, again, from your book, and that is the demand for beer was modeled by Hogarty and Elizanga with the function given by Q is equal to f of p. Q is equal to f of p, which we said that's the definition of the function. And if that is equal to 1 over p. So if my function is Q equals to f of p, which is equal to 1 over p, that's example 4. That's the function. The price was expressed in dollars. So the price is in terms of dollar. That's the small p. Therefore, how do we start? We already know what is Q. We already know from here that Q is equal to 1 over P. All we have to just take the derivative of this with respect to this. Pretend that this is X and this is Y. Y equals to 1 over X. How do we get the derivative? Using quotient rule, or even you can write p to the -1 and take the formula, the power rule formula. So here we will have, from here, we will have dq over dp. If you use the quotient rule, you will get -1 over p squared. Root of this times this would be 0, root of this is 1, times this would be -1 over p squared. So that's quotient rule is u prime v minus v prime u over v squared. So that's what we used it here. Then if you plug in the formula which we had it for elasticity was E, which is equal to minus P over Q, times dq over dp, for which we now have dq over dp, the derivative of Q with respect to P is nothing but how much? -1 over P squared. On the other hand, the Q is given to you. Q is 1 over P. So we take this and substitute here. Therefore, you will have negative times negative would be positive. P times 1 would be P. And then Q times P squared. But Q by itself is 1 over P. So this means P goes upstairs. It becomes P squared over P squared, which is equal to 1. So when E is equal to 1, in which case are we in? We are in the third case. That means the demand has unit elasticity. In this case, when you have E is equal to minus P over Q, and that will give you E is equal to 1. Now to go further, we would like to write a relation from P and Q and the revenue function. What is the revenue in general? We said that we have a cost function, that we have a revenue function, but the revenue is, in terms of Q, is just Q times P. Q is the quantity and P is the price of each item, and this will give you the revenue. Give you example so that you will see it. If you buy, for instance, if you buy 5 books, and each book or notebook, and each notebook is about $2, 5 times 2 becomes $10. So that $10 is your cost. Cost is $10. And then if you sell it for $12, that $12 is called revenue. Therefore, you have 12 minus 10, which is $2, would be your profit. So the revenue, on the other hand, would be this, because if you have 5 books, that is Q is 5, each one of them is $2. So you will have this multiply the Q by P, and you got the revenue. And this revenue actually, right now we could change it and write it down in terms of Q only, because P is given to you. How much is, or Q is given to you. If you look at it, the Q is 1 over P. So maybe we can use in terms of Q or in terms of P. Later on we will decide a little later. Right now we just take the derivative of this. So we take the derivative of R with respect to P, which means R prime actually. And if you take the derivative of this, would be how much? That would be derivative of PQ. Derivative of Q with respect to Q is 1 times P would be P times dQ divided by dP. And then plus Q. Q, because the derivative of this with respect to V would be Q. So you remember that we are taking the derivative of R with respect to P. That means Q is constant with respect to P. So if that is QP is like 2P, the answer would be 2. If it's 5P, the answer would be 5. And is the QP, answer is Q. Therefore, this is what we have so far. And if you look at it, here, if you just substitute for this, of course, they did in your book a little bit different ways. They multiply Q over Q, which is 1, doesn't make any changes. P times dQ over dP. So this is equal to 1, nothing would be changed. But that will make something easier for you if you take the Q from here and here out. and this one, Q is out. When Q is out, then what you have is P over Q times dQ over dP, and that's a plus Q. But this, we already know it from the definition. From the definition, that is equal to, that's equal to minus E. Because if you had a minus here, negative here, inside parentheses, that's exactly E, elasticity. Since you don't have it, so you multiply this by negative, that would be negative E. So this is negative E. Therefore, what you have is Q times negative E plus Q. And they both have Q in common. You can take the Q out. Negative E plus 1 is what you have it inside parentheses. And that's a Q is called common factor. You can write this as a 1 minus E for simplicity. You could change these two. You can do that, right? Negative 2 plus 1 is like 1, negative 2. Now, Q times 1 minus E. There are two cases, actually. If E is smaller than 1, like let's say E is equal to 0.7, then 1 minus 0.7 would be positive. So here the case would come. If E is smaller than 1, if this is smaller than 1, therefore what you have is R prime or dP, dr over dP, dr over dP, that becomes something positive. When dr over dP is positive, that means when R prime is positive, remember, then R would be increasing. So if you want to go look at this picture on page 778, therefore this is what we have. I can put the pictures here so you can see it better. So if this is E, for instance, if E is equal to 1 is here, and between 0 and 1, which means E is greater than 1, smaller than 1, I'm sorry, smaller than 1. If this is 1 and smaller than 1 would from here to here, then your function is increasing. It's going like this and stop here. So function is increasing because R prime is positive when E is 1. That's the first case. Second case, which we had, it was when E is greater than 1. If E is greater than 1, then what happens? If you look at actually here, the first derivative R prime was Q times 1 minus E, and E is bigger than 1, let's say 2 for instance, then 1 minus 2 would be negative. Negative times Q becomes negative, so this becomes negative. If R prime is negative, that means R is decreasing. So what we have is actually in this picture, again I come back to the picture, from this point on, because this is for E is equal to 1. When it's bigger than 1, that means you're going down. You're going down like this. Therefore, from here to here, your function is decreasing. So here R is increasing, here R is decreasing. When R prime is positive, when R prime is negative. First derivative positive, we have seen it in case of decreasing, increasing for a function. First derivative positive, function is increasing. First derivative is negative, function is decreasing. And at this point, E is equal to 1, which is, we are in the second case. So this would be your second case. This is the second case, actually. This is the second case. And the third one, when E is equal to 1, that would be the third case, which is this point. You will get only this point. It's not increasing, it's not decreasing, and it is maximum, actually, one of the critical points. So this is exactly what you have here, but they have a name for it. If E is smaller than 1, which means R is going up or R prime is positive, we say our demand is inelastic. So demand is inelastic here, inelastic. When R is going down, R is decreasing or R prime is negative, then after E equals to 1, which means E is greater than 1, then what we have is demand is elastic. So that's inelastic. Here demand is from here to here, from this point to this point, from this point to this point would be elastic. So we have two different types of increasing, decreasing of the same problem, and depends what do we need, what do they ask you. If they ask you where this function is elastic, you have to go by the second one. If they say where this function is inelastic, you have to go by the first one. Usually we start from the third one, then to get the result, whether first or second. So to make it things meaningful to you, and I give you another, but this time is a numerical example I have for you. That was in general discussion. I have a numerical example, which is actually example 5. So that example 5. Again, the problem is this. Assume that the demand for a product is Q equals to, so this Q equal to 216 minus 2p squared is given to you. That's a given function. That's a demand in terms of price. Small p is the price of each item, where p is the price in dollars. Question, can you find the price intervals where the demand is elastic? Remember, that was the second case. So we had the inelastic and elastic. And also where the demand is inelastic. So they are interested for both situation, both cases, case 1 as well as case 2, elastic and inelastic. Therefore, we have to start from our function, which is q equals to this, and take the derivative of this. dq with respect to p is how much? You take the derivative of this, and would be how much? If you take the derivative of this guy with respect to p, that's a constant, becomes 0. Derivative of this p squared is 2p, times 2 would be 4p, minus 4p. So that's the first derivative. This is what we have. First derivative is this guy. Then we write the e. What is e actually? E has a formula, which we started by this formula actually. Today we started from this formula, minus p over q, dq divided by dp. That's the formula for elasticity. That's the formula for elasticity. And now we have dq over dp. That means we have this, which is how much? Minus 4p. 0 is nothing. So we substitute this one here instead. And then we go from here. And also we could substitute for q. Q is how much? That's the q is. That's the q is. So we take this 2 and plug in here. So the answer becomes minus p divided by q, which is 216 minus 2p squared, times dq over dp, and we just got it, is minus 4p. That's a multiplication, remember, that's multiplication. Negative times negative is positive, and then what you have here would be 4p times p would be 4p squared divided by 216 minus 2p squared. Now, to solve a problem like this, we go backward. We start from the third case, which was E is equal to 1. Then we find, so let's assume that E is equal to 1. That's the third case. If E is equal to 1, how much would be a small p? So if assume that E is equal to 1, then how much is the p? P is how much? A small p. Then from there we can go to first case and the second case. When that's equal to 1, how do we solve it? One way is to multiply both sides by 216 minus 2p squared, or simply cross multiplying. That's the best way. Cross multiplying is another way to solve this problem. 4p squared times 1 would be 4p squared is equal to 216 minus 2p squared. You add 2p squared to both sides, this would be 6p squared, because this guy adding 2p squared, 6p squared, like 2 apple and 4 apple would be 6 apple. is equal to 216, and divide both sides by 6. 6 cancel. So P squared would be how much? 216 over 6 is 36. Therefore, P is equal to 6. So for this problem, once you have a given equation, Q in terms of P, you try to find P by assume that E is equal to 1. In other words, we assume the third case, that you need elasticity, and then we go to the first case and second case. Therefore, P is equal to 6. We have two cases. First, let's assume that anything is smaller than 6, like 5 or 4 or 3 or 2, and here they assume P equals to 1. See what happens to E. If P is equal to 1, it could be 2, it could be 3, you could assume anything smaller than 6. And then what happens to E? Well, you got to substitute here the answer that you have here. So you have 4 times 1 squared, that's a 4P squared, divided by 216 minus 2 times 1 squared. So we substitute here, actually, in here. And that would be 4. This is something bigger than 4. Numerator is smaller than denominator. So this becomes smaller than 1. Anytime numerator is smaller than denominator, therefore, whatever the number is, we are not interested what number do we get, but actually you can substitute for it. You will get actually 4 divided by 214, which is smaller than 1. What happens when E is smaller than 1? And if we go by the definition, when E is smaller than 1, then demand is inelastic. So in this case, you have inelastic. Then you go to the second case, which means when P is something bigger than 6, like 7, 8, 9, 10. I think they assumed E to be equal to 10, for instance. If E is equal to 10, what happens? To the same formula, you will put 10. So you will get, if P is equal to 10, then E becomes how much? 4 times 10 squared over 216 minus 2 times 10 squared. And that will give you 100, 400. And the bottom will give you 216 minus, that's 100 times 2 will be 200. So your answer becomes like 16 in the bottom, but the top is 400. So what happens if you have a fraction, the numerator is larger than the denominator, that is bigger than 1. So that's the case 2, which means in this case, by definition, if you look at it, we have the second case was when E is greater than 1, then demand is elastic. So demand is elastic, and that's what they were asking for. So we are done. So they said find P for which the demand is elastic and inelastic. So that was the result. I think I better stop here, and then we can discuss it another section for the next time. And good luck to you, and I will see you again next time. Thank you. Bye bye now.